So we're going to cover something about the stick diagrams. Did you watch the video from yesterday, the lab? I mean, if you haven't, after this class, make sure you will watch that video, which is on the lab's website. Right here, video notes, right? Watch it. And this lab, so yesterday's lab was a 2-week lab, but you will find out that actually next week we don't have a lab. You know what I mean? That was a career day, I guess. So you are supposed to take a break, right? So nothing, so you don't have to do it on Tuesday, but you have to do it somewhere else, at some other days. And because it's going to be due on the 22nd, which is Monday after that week, right? See here, no lab tomorrow. That's for next Monday, right? So no lab on next Tuesday. Yep, that's everything about the schedule recently. Do you still remember the logic for Axor Gate, which is trivial, I think, right? Axor. A not B, B not A. Or Axor. How many of you didn't watch the video from yesterday? Okay, yeah, let's start from here probably, it's better. AOI stands for AND, OR, invert, logic. So Pmoses are being used to pull the output to the VDD, and NMOSes are used to pull the output to the ground, right? So that's why for the NAND gate, we have this, no, this, so A is shorted to A, B is shorted to B, ground, and here's output. It's A NAND, right? So A and B bar. So for NOR, you just put the 2 Pmoses in series on the top and 2 NMOSes in parallel at the bottom. Okay, so here's one thing you want to memorize because it's been verified so many times. You know, you can, every time you use it, it's going to be correct. So the best way to implement it in the future is just to memorize it, right? After you can understand this, keep in mind, every time when you are applying AOI logic, just for a complex logic expression, use CMOSes instead of using gates. You want to look at the bar first. So find out the bar. If you don't have a bar, create a bar. Just put 2 bars on top. So invert, which is still the same original logic, right? So now we don't have to do it because I have a bar on the top. Okay, so right below the bar, you have an AND logic. If you see AND logic, then you need 2 Pmoses on the top in parallel and 2 NMOSes at the bottom in series. Keep in mind, always. Whatever underneath the bar, if it's AND logic, then Pmos in parallel, NMOS in series. If it's OR logic under the bar, that will be, it's an OR logic under the bar, then Pmos is in series on the top, and NMOS is in parallel at the bottom. Where did we get this conclusion? Watch the video from yesterday. Okay, it's going to take another 30 minutes to do that one more time. So that's NOR. Is that clear? Just remember that. If you have an AND logic, then you have to have the Pmos. The Pmos is in parallel to pull this, because this result, you know, A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. These are all the possible input combinations. And you are getting what for the NAND gate? 1, 1, 1, 0, right? That's a NAND gate result. So the result or the output has ones and zeros. Has ones means you have to, have Pmoses to pull it up to 1, and have two Nmoses to pull it down to the ground. So that's why you need both Pmoses and Nmoses. All right. And for the unlogic underneath the bar, the Pmoses has to be in parallel, because if you look at the logic here, whenever it's being pulled up to VDD, which means you have to use the Pmoses to pull it up to VDD. Why? Because the Pmoses are good at pulling the output to the VDD. If you forget it, just watch the videos of one of the lectures I forgot. I think I have mentioned this for a few times. All right. You need the Pmoses to pull the output to VDD, so you can implement all these results, or implement this set of logic in the truth table. And why Pmoses has to be in parallel? Because if you look at the inputs, either one or both of them are on, then it's being put to VDD. So that's why the logic is implemented. See, 0, 0, both are on, boom, both are open. Or just one of them is on, then you got at least one channel to pull this to VDD, because this has to be low in order to have a positive VSG to turn on the Pmoses. That's for this one logic, right? For the 0 logic, you have to have both A and B to be 1. So you have to turn on both the Nmoses on in order to open this channel, entire channel, because these two Nmoses are in series. So you can have an open channel to pull this to the ground, okay? That's how this is designed in this way. Since this is our needs, right? We need this logic for the circuits. And then people are thinking about how can we design the CMOS circuit, and these are the materials we have. Or you can see these are the tools we have in the toolbox. So let's just build a circuit to implement this truth table, and that's how that works. So this is how we design this non-logic to implement this truth table. Same thing for the NOR gate as well. Okay? Because the conclusion here is, if you have an unlogic, below the bar, then you have to have two Pmoses on the top in parallel and two Nmoses at the bottom in series. If you have OR logic below the bar, then you have to have two Pmoses on the top in series and two Nmoses in parallel at the bottom. And this applies to any other complex logic expressions. But you just need to put everything underneath the bar, only one bar. That's the conclusion. Okay? Why is that? You just verify it. It works all the time. And if you want to know where this comes from, just watch the video from yesterday, okay? I'm going to show you one more example. Probably a couple of other examples for this. The most common one, XOR. Y equals to A, not B, or A, B, not, right? That's XOR logic. Or sometimes we just write it as A XOR B. You have A and B. You have to invert it. And a B. So this part is here. And for this part, you need an A and B not. And or. Wait, no, and, sorry. That's this. And the final results should be OR together, so we're getting A XOR B. Okay. So if you do the layout, Pmos on the top, Nmos at the bottom, stick diagram, introduce a VDD, that's A inverted, and same for B. So this represents a Pmos, and this is Nmos in a stick diagram, just to simplify the layout. Right? So you got an A, you got a B getting inverted, and you need an AND gate AND gate. You need a NAND gate and inverted, right? So that will be, so draw the NAND gate first. You have two Pmoses in parallel. So introduce a VDD. So the current is being, so you got two branches to flow the current. So these are the two Pmoses and being merged at this point, right? So these two Pmoses are in parallel, and you need a two NMOSes as well, but these two NMOSes are in series. Okay, these are the gates. Two inputs for the NAND gate, and here's the output for the NAND gate. And you want to invert it because it's an AND gate, it's not a NAND gate. So here's the AND gate. And you need two AND gates and one OR gate. It's be a lot of work here, right? And you need an OR gate. So Pmos is in series and NMOS is in parallel. In series, in parallel, these are the two inputs, and that's the output, and being inverted. So that's the OR gate. And now just make the connections. You have A is being inverted, so that's A naught, which is here, as one input for the AND gate, for one of the AND gates, right? And then B went to the other input of the AND gate, A naught and B, so you got this part, so the output of the AND gate, which is here, right? And then you have A and B naught, right? So A is here, B naught is here, and you want to AND them together. And here's the output for this guy. So these two outputs are being ORed, and you get output. So what is this output? A XOR B. That's the XOR gate in the layout. In the gate level, right? So if we look at this Axor gate, which is actually this, and if we use what's that called? De Morgan's law, bar, right? So it's not changing the logic. Wait, so let's come back to this. I know this can be confusing for some of you guys who didn't watch the video yesterday, and also the video on Monday. No, last Friday actually. So that's P2. That's one Pmos. That's the gate, right? And that's one NMOS. So these two circles represent the N plus of the NMOS. Here's a little gate, right? So if you are still remember the layout in the electric VLSI, it looks like this, right? With the connections on the two sides. That's one Nmos or Pmos. So using the stick diagram, we can just draw the layout really quickly on the paper before we use the layout tool to place the transistor in there and make the connections. So this can simplify the design process. That's why we use stick diagrams, sticks. Right? So this is Nmos in the library in your electric VLSI tool. And what we do, we just use two crosses like this and one stick in the middle. So this is a gate, which is the same as a gate in the middle. And these two are the two connections here, Vs and N plus. Right, so this is one Nmos. Okay. For the Axor gate, I keep the overall bar on the top and just convert this guy to something. Let's see how that works. So according to De Morgan's law, if I want to convert this one, I need to split the bar and change the sign. So what I'm getting is A like this and change the sign like this. And this equals to still keep the bar on the top and do the same thing, split the bar, change the sign. So I'm getting this. Which is zero, zero. So XOR is actually XNOR not. So if you want to implement XOR gate, you can directly use XNOR because XNOR has a bar on the top. You invert XNOR, you're getting XOR. So just look at this part, like just what we just mentioned. If you have unlogic, enter the bar, what you need for the Pmos and what you need for the Nmos. Unlogic. Pmos in parallel and Nmos in series, right? Same here. And overall for these two blocks, you have OR logic. So these two blocks actually need to be in series on the top of the Pmos and in parallel at bottom for the Nmos. So let's just assume these two logic expressions are two black boxes. So you can imagine that this is a NOR logic because or not. That's a NOR logic for these two blocks, these two black boxes. So that will be something looks like this, right? In parallel, in series. No, in series, in parallel for these two boxes. So now I want to implement this logic inside each box over here. So now it's unlogic. So in each box, unlogic should be in parallel, right? For Pmoses. This is A, this is B, because these two, this is unlogic, so these two Pmoses should be in parallel. What about this? This box, because this box is this box, and this box is this box, right? Same. In parallel. And because these two boxes is the OR logic on the top, so that's why it should be these two boxes should be in series. At the bottom, this is unlogic, so it should be in series for the two Nmoses. Same here, same here. Make the connection, ground it. And what are these two? A and B. A naught, B naught. And make the connection. And make the connection. Here is the output. What is the output here? A. So what is the output here? AX or B? So here's a question. Let me double check this really quick. Yeah, so for this part, so I have one wire, another wire, another wire, another wire. I have 4 wires being shorted together. So just merge it to one wire, right? It's not making any differences. Is that clear? No, still confusing. So you can simplify this circuit and you draw the stick diagram of this guy. It's going to be way simpler than this. This is from the gates. You have to draw every single gate. But if you do it here, it's going to be way easier. So let's see if we can, let's do it. Let's draw the stick diagram probably on Monday, since I want to give you enough time to do the quiz. Give you 20 minutes to do the quiz. We probably don't need that much time. Oh, that's 30 minutes from now. So I still have 10 minutes to run the stick diagram. Sorry for that. I'll give you 25 minutes about that. I'm going to spend another 5 minutes to draw the stick diagram so you can see the difference. Because on Monday next week, if I start working on this again, probably have forgot everything what I have done here. Okay. So let's make this schematic clearer. I mean, so it actually looks like this if we clean up all these wires. And magically, this is AX for B. Now let's draw the stick diagram. See how that works. So first, how many Pmoses do we have on the top? I guess 4, right? So I have 2 rails, VDD and ground. I'm going to start doing this one. 1, 2, 3, 4 Pmoses. I'm going to try this first, see if that works. Sometimes it doesn't work because I have to short all these terminals together. 1, 2, 3, 4 Pmoses. I'm trying to do this part layout for now. So you have these 2 Pmoses on the top in parallel. So what I can do is I can introduce the VDD from here. And it flows to this part, so it runs through 1 Pmos because it runs through 1 gate here, another gate, and merges at this same point. So I'm going to merge it at 1 wire. And then what? Then these 2 are in parallel as well. Can I still make it work in this way? Let me see. Is that possible? Seems like you see this point, this joint here is this point, and now I need to split this wire into two. So if I connect this part to here, then this is still being shorted. They are sharing the same node, so it's not working. So the worst case is not working, then you just do two of them in parallel. Just do two of them together. So which will be, see right now you cannot split it because too many points that are being shorted together. So if you cannot do that, you just do this. In parallel, merged. In parallel, merged. Oh no, this is not from the VDD. So this part, get into here, and then in parallel, and then introduce one wire to the bottom. And you have 4 Nmoses at the bottom. 1, 2, 3, 4. 1, 2, 3, 4. If I connect this part to here, then so this node is this node, right? No, you don't do that. So it should go to here. See, this will work. This is being shorted to this Nmos, and the current will go to this direction and this direction. And then you introduce another wire to here. So it goes to this direction and this direction. And merge to here, and you ground it. And ground here as well. It's recorded, so hopefully it's going to make sense at some point. Any questions? No questions? Just want to do the quiz. Do it.